All right, guys. The next couple videos, I'm going to cover 1-3. Okay, so we're talking periodic trends. All right, so a lot of you probably already know all the trends. We cover them in Chemistry 1 a lot, but what we want to understand is that it's not about knowing what the trend is and being able to rank atoms, in order of size or ionization energy or electronegativity. That's not about that. The kind of questions you're going to have to answer on the AP exam are using structure to explain the trend. And then understanding what it means. Like, so if I know that this is more electronegative than that, so now I know this bond is more polar than that bond, how does that affect the intermolecular forces between the particles that have that type of bond versus the particles that have that type of bond? So it really comes down to be a structure thing. So that's why, like in 1-2, we talk about atomic structure, ionic structure if we gain or lose electrons, but the structure of an atom or an ion. Now we want to use the structure of an atom. So what does that mean? It means the number of protons in the nucleus. We don't really care about the neutrons right now. So the number of protons in the nucleus, and then how many electrons we have, and then where those electrons are within the cloud. So are we in energy level 1, energy level 2, energy level 3? And then we can focus in on that energy level. So I might be in energy level 2, but am I in an s orbital or am I in a p orbital? And that might explain why this is less than that or this is more than that. Okay, so it's using structure, electronic structure, so electron configuration, orbital diagrams, and number of protons in the nucleus, so nuclear charge. So 1 proton is +1, 9 protons is +9, 88 protons is +88. So the charge of the nucleus, what does that do to the attraction the electrons have to the nucleus? Does that make it smaller? Does that make the cloud smaller? So a smaller radius, does it make the cloud bigger, a bigger radius? If I have a smaller radius, what does that mean about how much energy I have to put in to remove an electron from that cloud, that kind of thing. So using structure to explain the trends, not using the trend to rank things. Okay, so Chemistry 1, I know what the trend is, I know what the definition is, and I can rank things in order of greatest radius to smallest radius, or highest ionization energy to lowest ionization energy, or something like that. In AP Chemistry, we want to use the structure of the atom and our basic understanding of Coulombic attraction and repulsion to explain the trend. Okay, so that's the idea. So this video is going to cover atomic radius and ionization energy, and then the next video is going to cover the rest of the trends. Okay, so let's jump into it. All right, so again, here are all of our trends, and again, this video is just going to focus on these two, atomic radius and ionization energy. But we want to know electronegativity. That's going to be important as we move forward and we start talking about polarity and intermolecular forces and dipole-dipole interactions and hydrogen bonding and all that stuff. So that's going to be important then. Then a couple other things we need to know about electron affinity. Maybe we just need to know the definition, and that's about it, and what the trend is. We're not going to spend a lot of time. You're not going to get questions on the AP exam about electron affinity a lot. We just kind of have to know what that means. Ionic radius is going to be important, and what I wrote here is a big deal. All right, so if we're talking about the radius of an ion, don't say atomic radius. Atomic means atom, means neutral. Ionic means charged particle, means not neutral. So when I say atomic radius, I'm talking about something. I'm talking about a particle that has the same number of protons and electrons, so the overall charge is neutral. But if I'm talking about an ion, then I'm talking about something that has a different number of electrons than protons, and that's going to affect the size of the cloud. All right, so ionic radius isn't the same trend as atomic radius. Okay, and then we'll talk about metallic reactivity and non-metallic reactivity. But this video is going to focus on these two. But again, it's all about the structure, right? It's all about using structure to explain the trend. Okay, so that's why I highlighted it here. Okay, so you need to know the trend. You need to know, as I go left to right, across a period, across a row, what happens? Does it increase? Does it decrease? As I go down the periodic table, as I go down a group, does it decrease or does it increase? So you need to know that trend. And so you also want to kind of know it diagonal. I get this all mixed up because of Harry Potter now. Diagon Alley. So you want to know it diagonally. So like if I start down in the lower left-hand corner at francium and I go up and to the right all the way to helium on my periodic table, I kind of want to be able to explain the trend. It's either going to increase or decrease depending on what the trend is. And so a lot of times helium is either the biggest or the greatest, and francium is either the greatest or the smallest, depending on what trend we're talking about. So if I know helium is the biggest or whatever, or greatest of whatever trend I'm talking about, then I know as I go left to right and go up, it must be increasing. But if francium is the biggest, then as I go left to right, it must decrease, and as I go down, it must increase. So that kind of thing, all right? So like in the past, you might be asked which atom is bigger, potassium or sodium, right? And if I asked you why in chemistry one, if you said because it's further down on the periodic table, I might accept that as an answer because it's really just kind of about the trend of that. Do you know the trend? But we really, if in AP chemistry, if you're asked why is a potassium atom greater than have a bigger radius than a sodium atom, you can't say because atomic radius increases as you go down the periodic table. That's true. Atomic radius does decrease as you go down the periodic table, but you have to use the structure of the atom to explain why potassium has a bigger radius than sodium. Okay, so the answer we're really looking for in AP chemistry, why is potassium bigger? It's because potassium's valence electrons are in energy level 4 or shell 4, and sodium's valence shell is energy level 3. And so the higher the energy level, the further away you are in the nucleus on average most of the time. And so that's why as you go down the group, you gain an energy level. If you gain an energy level, your radius gets bigger, right? So using the electronic structure, the electron structure of an atom to explain the trend, okay? And so what it's going to come down to, especially when we're talking about radius and attraction to the nucleus and all that stuff, it's all Coulomb's law, right? So we have to have a good understanding of Coulomb's law. So the more protons I have in the nucleus, the greater the nuclear charge, the stronger the attraction there is to the electrons. But then there's a balancing act. As I gain another energy level, those electrons are now in the higher energy level are now further away from the nucleus, and the further the opposite charges get from each other, the weaker the attraction. But not only that, we have what we call shielding. So you have the valence shell; those are the outermost electrons. They kind of set the radius, right? And they're attracted to the nucleus, but in between them and the nucleus, you have your core electrons. And electrons repel each other. So you have this, what we call shielding or interference or blocking, however you want to call it, of the core electrons shielding the valence electrons from the nucleus. So I might have a really highly charged nucleus, like a plus 87 in francium's case, but it's still going to have a bigger radius than most of the other atoms because it has so much shielding. And so it only has one valence electron, and that valence electron is in energy level 7, but there's so many core electrons that are shielding that valence electron from the nucleus, even though it's a plus 87. And so it's going to be pushed further away and thus having a bigger overall radius. Okay, so remember when we talk about radius, it's really just the valence shell that sets the radius. It's the valence shell that sets the radius. Okay, because if I have valence shell, if my highest energy level is 7, then all of the electrons in that energy level are going to be shielded by all of those 6 energy level of core electrons. Okay, and so it's the valence shell that's going to end up setting the radius. So it's the valence shell and its attraction to the nucleus versus its repulsion or shielding from the core electrons that end up setting the radius. So you have this balancing act between attraction to the nucleus and repulsion from electrons within within the same orbital versus electrons that are closer to the nucleus than further away. So the explanation for most of these trends comes down to how attracted the electrons are to the nucleus. And what's that going to depend on? How close they can get. The closer, the stronger the attraction, but then also the charge of the nucleus. The higher the charge of the nucleus, so the more protons in the nucleus, the stronger the attraction. All right. So atomic radius, you might remember the snowman, right? It's the size of an atom. And again, by definition, an atom has the same number of protons and electrons. Okay? And, as you go down, it gets bigger. We know that, right? A snowman gets bigger as you go down. But if we knock the snowman over, as we go left to right, it decreases. Okay? So we should kind of understand as we go down, it gets bigger because I gain an energy level. And so the more energy levels I have, the bigger my radius. But then why does it decrease going across? Because if you looked at the masses, neon is much more massive than lithium, right? And look at lithium. Lithium is much lighter than krypton, but krypton still has a smaller radius than lithium, okay? Now, we just need to know the trend as we go down, left to right. So diagonally, we have to know it increases this way. Diagonally, it decreases this way. But I would never compare, on this diagonal. I would never ask you to do that because you'd have to know more, right? So, but why does it decrease as you go down? Well, as you go across from left to right. Well, you don't have any more energy levels, right? All of these in row 2, their valence shell is energy level 2. All of these in row 3, their valence shell is energy level 3. Row 4, energy level 4. So you still have the same number of core electrons. So what that means is as you go across, shielding stays about the same because you have the same number of core electrons, but you gain a proton in the nucleus. So that extra proton in the nucleus increases the attraction of all the electrons in if we're looking at this row, energy level 2, right, increases the attraction to it, and it pulls those electrons closer to the nucleus and making it have a smaller radius. Okay. Now notice there are some exceptions, right? Look at like fluorine versus neon. It gets actually a little bit bigger, right? Chlorine versus argon. So there's always a few exceptions. You don't need to know those exceptions. When we get to the ionization energy trend, you'll have to know them. Notice that what the radius is measured in, it's picometers. So it's really small. What is that, 10 to the negative 12 meters? So, atoms are small. All right, notice the transition metals aren't in there because the transition metals, they're a little weird. So, you can assume they follow the trend, but transition metals in the same row generally have similar size. They're not going to be that big of a difference. Okay. So why does it increase going down? You gain an energy level. Okay. Why does it decrease going across? The nuclear charge increases. You gain a proton, the nuclear charge increases, the electrons get pulled closer to the nucleus. Okay. And if the electrons are closer to the nucleus, it's the electrons that set the radius. So if the electrons are closer, you have a smaller radius. All right. So let's talk ionization energy, because this is going to be an important concept, and you will be asked these questions. Like, you need to know the difference between, ionization energy, the trend, which is just talking about first ionization, versus, subsequent ionization energies. You have to know what that means. And you have to be able to explain the exception, and you have to look out for the exceptions to the ionization energy trend. Okay? So when we say what's the trend for ionization energy, we mean first ionization. And all first ionization means is I have a neutral atom. To ionize it means to remove one electron from that atom and make it a +1 ion. So we're talking about the removal of one electron from the atom. Okay, that's first ionization. So you might already know the trend. It's opposite atomic radius. So as I go left to right, the radius gets smaller, but ionization energy gets larger. As I go down, the radius gets bigger, but ionization energy decreases. So first ionization energy generally will decrease as you go down a group, and it will increase going left to right across a period. But notice I said generally here, generally increase. That means that as you go down, there's no exception. As you go down, it gets easier to remove an electron. So ionization energy decreases if we're talking about first ionization. Okay. But as I go left to right, especially in periods 2 and periods 3, so we're talking about lithium's row, so lithium to neon, and sodium's row, sodium to argon, we do get exceptions to the trend. Okay, and it happens twice within a row, 2 exceptions within a row. Okay, so first we're looking lithium to neon, and then we're looking sodium to argon. So here's a chart of first ionization energies. So what I want you to notice here, here's lithium. It has a pretty low ionization energy. And as I go all the way to neon, so that would represent one row of the periodic table, it gets bigger. So look, the general trend is it increases. Same thing, sodium to argon, the general trend, it increases. But we do have a couple of exceptions. The exception is between, so this would be beryllium and this would be boron. So as I go from beryllium to boron, it actually goes down and then it goes back up again, right? And then this would represent nitrogen and this would be oxygen. So nitrogen to oxygen, it goes down. And notice the same thing happens here from sodium to argon. As I go down, as I go from magnesium to aluminum, it actually decreases. And then again, phosphorus to sulfur. And if you look at your periodic table, it happens in the same spot. Okay, so both exceptions to the trend happen in the same spot in row 2 and row 3. And it's not a coincidence, right? It's periodic pattern, right? Periodic table. Okay. And so we might not have, talked about this, but the closer the electrons are to the nucleus, generally the harder it is to remove because they're more attracted, right? It comes back to Coulomb's law. So why does ionization energy increase going left to right? As I go left to right across a row, the electrons generally get closer because I have a smaller radius. And because of that, the electrons are going to be more attracted to the nucleus because they're closer. And the closer opposite charges get to each other, the stronger the attraction. So the more difficult or the more energy you have to put into removing the electron, right, in general. And as I go down, the radius gets bigger, right? So I might have more protons in the nucleus as I go down the periodic table, but because my electron cloud is getting bigger, the electrons are further away from that nucleus, making them easier to remove. They're not as attracted, right? It comes down to Coulomb's law, all right? Okay. So again, beryllium to boron, exception. Nitrogen to oxygen, exception. And if we looked at the next group, this would be magnesium to aluminum, there would be a dip, and then phosphorus to sulfur, there would be the same dip. Okay, in general it increases, but notice we have a couple dips, okay? All right, so between beryllium and boron it decreases, between nitrogen and oxygen it decreases. Now, it goes against what we already know, right? We know that beryllium has a larger radius than boron, right? We could go back to this, right? Boron has a smaller radius than beryllium. We know boron has one more proton in the nucleus than beryllium. So this has a +5, this is only a +4, right? And we know oxygen is smaller than nitrogen, and oxygen has one more proton, a +8 versus a +7 nucleus, right? But ionization energy is telling us it's actually more difficult to remove a nitrogen electron than an oxygen electron. And again, we're talking about the first electron. And the same thing, it's more difficult to remove a beryllium electron than it is a boron electron, even though beryllium has a +5, boron has a +5 and beryllium has a +4, even though oxygen has a +8 and nitrogen has a +7. Okay, so again, it comes back to structure. And so the +8 of oxygen is still not enough to make it harder to remove that first electron from oxygen. So there must be something within the electronic structure, the electron configuration, that's the reason for why it's easier to remove an oxygen electron than a nitrogen electron, right? And so let's look at it. So why do you think it's happening? What's the difference between beryllium and boron here? Okay, well, the thing to notice is the first electron being removed from boron is a p electron, but the first electron being removed from beryllium is an s electron. And remember, if we had drawn, instead of just an orbital diagram, if we drew an Opal diagram, remember the 2p is slightly higher in energy than the 2s. So even though there's a +5 here and a +4 here, because there's a slight difference between the s orbitals and the p orbitals, it actually makes it a little bit easier to remove that electron than one of those electrons. Now, as we go from boron to carbon, it gets much more difficult, because now we're not talking about the difference between removing a p electron and an s electron. Now we're talking about the difference between removing a p electron, but now we have, instead of just one more proton in the nucleus, as we go to carbon, now we have 2 extra protons in the nucleus, and that higher nuclear charge is enough to make it more difficult to remove the electron. So we only get that one exception when it's a difference in one proton and the difference between removing a p orbital electron versus an s electron. Okay, and then remember, we get another exception to the trend here as nitrogen to oxygen. So what's going on there? Well, both electrons, the first electron being removed from nitrogen would be from the 2p sublevel, and same with oxygen, it would be from the 2p sublevel. But what's the difference? Well, nitrogens are going to be non-paired. So all the electrons in the p sublevel for nitrogen are not paired. But oxygen does have an electron or 2 electrons that are paired in one of those orbitals. And remember, we get electron-electron repulsions within that orbital. And so even though oxygen is a +8 and slightly smaller, because we have those extra electron-electron repulsions in this orbital that we don't have in one of the p orbitals from nitrogen, it's actually going to be a little bit easier to remove that electron than one of those electrons. Okay? So that explains the trends. And so the same thing happens when you go to the next row, when you're talking about, this would be magnesium and this would be aluminum. What's the difference there? Removing an electron from 3p versus 3s. And then the difference here would be, again, phosphorus would have all ups and no paired electrons, but sulfur would have one paired, and those little extra electron repulsions in one of sulfur's p orbitals is enough to make it a little bit easier to remove than a phosphorus electron, even though the sulfur has a +16 nucleus and phosphorus only has a +15. Okay? All right. So the other thing we need to know about ionization energy is successive or subsequent ionizations. So, this right here, this equation would represent the first ionization of carbon. So when we talk about ionization energy, we talk about first ionization energy. We're talking about something like this. I have neutral carbon, and I remove an electron, and now it's becoming a +1 cation. Okay? Now, this would represent second ionization. So the removal of a second electron. So going from a +1 to a +2. And then we would have third ionization and fourth ionization and fifth ionization. And the first thing to notice is, as you keep removing, and you could have an ionization for every single electron that atom has. So carbon has 6 electrons, so I could have 6 ionizations of carbon, right? Francium has 87 electrons. You could have 87 ionizations of francium, okay? But the first thing to notice is, it doesn't matter first, second, third, fourth, fifth, sixth, seventh ionization. It always gets more difficult to remove an electron. So what I want you to notice is, for lithium, right? First ionization, second ionization, third, these numbers are getting bigger. It always gets harder to remove another electron. And think about that, right? Right? Why would that be? Well, as you remove an electrons, the cloud kind of gets smaller. The remaining electrons are going to be a little bit more closer to the nucleus on average. They're going to be more attracted. It's going to get harder, right? Another way to think about it is, right, if you remove an electron, now I'm +1. And now you're removing an electron from something that's positively charged. The electron is going to be more attracted to that positive charge. And if I keep removing electrons, the positive charge builds up. And so it's just going to keep getting more difficult and more difficult to remove an electron from something that increases in its positive charge, right? The main thing to notice, though, for successive ion, and notice notice the exception, right? Boron, based on the trend, should have a higher ionization energy, first ionization than beryllium, but notice beryllium is actually a little bit greater, right? And then same thing with nitrogen and oxygen. Oxygen has a slightly lower first ionization than nitrogen, so it goes against the trend. So that's the exception again. But the main thing about successive ionizations is what you want to notice is the big jump. The big jump shows you where there's a difference between removing a valence electron versus a core electron, right? Lithium has a very low first ionization, but notice its second ionization is really big compared to that first. And it's really big compared to that first because this electron being removed would be from energy level 1. This electron's being removed from energy level 2. This is a valence electron. This electron is now removed from energy level 1, and so it's a lot closer to the nucleus. Beryllium has 2 electrons to remove, so notice where its big jump is. So it always gets more difficult, but there's not that big of a jump between this number and that number, but then there's a huge jump between this number and that number. So these are the valence electrons for beryllium. This is a core electron. Boron has 3 valence electrons. So you're not going to get a big jump in ionization until ionization 3 and 4, right? Because these would be the 3 valence electrons removed, and this would be a core electron being removed, okay? So when you're given successive ionizations, what you want to do is look for the big jump. The big jump will tell you how many valence electrons you have, and that'll tell you what group you're in, right? If I have a big jump between ionization energy 2 and ionization energy 3, that means I have 2 valence electrons. I know I'm in group 2, right? If my big jump isn't until ionization energy 5 and 6, then I know I must be in group 5A, nitrogen's group, right? Because I have 5 valence electrons. And then this would represent a core electron. So that's really kind of what to look out for successive ionizations, okay? All right. So that's a long video intro to the ionization energy stuff and atomic radius. The next video is going to cover the rest of the trends. All right. Peace out.